Hello everyone. Today I would be discussing one of the problems of Codeforces around 930. It was organized by the Forces community. Like I think the problem will be E in due to round and C in due one round. The problem name is Pokemon. Let's get started. Problem statement: you are at a dueling arena and you also possess nine Pokemons. Initially, only the first Pokemon is standing in the arena. Each Pokemon has M attributes. The Jth attribute of the ith Pokemon is Aij. Each Pokemon also has a cost to be hired. The ith Pokemon's cost is Cij. You want to have an nth Pokemon in the arena. To do that, you can perform the following two types of operations any number of times in any order. Choose three integers I, j, and k, where I is between 1 to n, j is between 1 to m, and k is greater than 0, and increase aij by k permanently. The cost of this operation is k. Choose two integers I and j, where I is between 1 to m and j is between 1 to I is between 1 to n and j is between 1 to m, and hire the ith Pokemon to duel with current Pokemon in the arena based on the jth attribute. The ith Pokemon will win if Aij is greater than equal to the jth attribute of the current Pokemon in the arena. Otherwise, it will lose. After the duel, only the winner will stand in the arena. The cost of this operation is Cij. Find the minimum cost you need to pay the nth Pokemon stand in the arena. The constants are Cij is between 1 and 1 Aij is between 1 and 1 Sum of n into m is less than equal to 0.4 million for a particular test file. Like to solve this problem, like the way I will solve is I will model it as a shortest path finding problem. The n nodes will correspond to each Pokemon. The source node would be node 1, the first Pokemon, and the destination will be node n, the nth Pokemon. The question is how do we handle Aij and Caij over here? So like the way to do is like we will add edges between all the Pokemons for each of the attribute over there. So for example, if you look at j equal to 1 attribute, c11 is 2, c21 is 2, and c31 is 6. And as from 2 to 1 denotes the cost to replace 2, like cost to replace 2, which is who is in the arena right now, with 1 that we want in the future. So for example, if currently 3 is in the arena, and if we want to have 2 in the arena based on the first attribute, then we will have to change C21 to 6, and like that C21 and C31 is equal. So like the cost here is this as denotes 4. Similarly, like moving for the next attribute type, if you want to replace one Pokemon with the other based on j equal to 2 attribute, then in the given sample C2 is 3, C22 is 9, and C32 is 1. So if currently 2 is in the arena and we want to replace it with 3, then based on the j equal to 2 attribute, then we should make C21 as 9. So if 2 is in the arena and we want 3 finally in the arena, then the cost is 8 over here. Similarly, if 1 is in the arena right now and we want to replace it with 3 in the arena, then we should have 3 to at least 3 over here. So in that case we would have to increase this by 2 and the cost would be 2. So if 1 is in the arena and if we want 3 in the arena, then we should have replace it by 2. Note that this does not involve the cost of hiring the Pokemon. We will deal with it later. And if we want to look at based on j equal to 3, then C13 is 1, C23 is 9, and C33 is 7. So if currently 3 is in the arena and if we want 2 in the arena, then already it is 9 is greater than 7, so we don't need any new cost over here. So 3 in the arena, and if we want 2 in the arena, no additional cost is required. But alternatively, if 2 is in the arena and we want 1 in the arena, then we should make 1 3 as 9 over here. So the cost to replace 2 with 1 is 8 over here. And the question is assuming that we have hired all the Pokemon, and if we run the shortest path finding algorithm from 1 to n in this graph with 2 into n into m, which is around 18 edges, The shortest path length will be minimum number of times we will have to increase different aij's to reach n from 1. And like take a pause and see like why does it holds. And like I will move to the next part. This is because if Pokemon U is in the arena and if we want to replace it with Pokemon V using skill J, then we will have to increase the skill by the skill of with Pokemon J skill of with Pokemon by max 0 UJ minus UAV. That is, if VJ is greater than equal to UJ, we do not need to increase UJ, like which is the UVJ, it should be VJ, which would be the current Pokemon. Otherwise, we will have to increase it by AVJ minus, it's like it should be AUJ minus VJ, so that the skill of both the Pokemons are equal. Like initially, if we have U in the arena and if we want to replace it with V using skill J, then AVJ should be greater than equal to AUJ. So like there is a typo over here, like that I will fix it once before I publish these slides over there. And like the next question is, how do we handle hiring of the Pokemon? Like the idea is for all the edges from U to V, we add an edge CV cost to it corresponding to hiring Pokemon V. So like right now, like we had UV, like there was some different cost to it. Like we should add CV to all the edges which come into V, so that whenever like V finally gets replaced, like CV would be the cost associated with it. So like if I move back in the example, like if the let's say the cost to hire two, like let me just look at what was the cost once. Like the cost to hire Pokemon is 2 over here. So if currently 3 is in the arena and if we want 2 in the arena, then we should pay 0 cost for increasing the attribute and like plus 2 to hire the second Pokemon. So overall this would be 2 over here, this would be 4. Like this would be 2. Any edge coming to 2 will have plus 2 added to them. And that would be essentially the idea. Like this would definitely solve the problem, but in the given constraints it will definitely get a TLE. But and like what, like if this leads to an extra cost if you want one of the hired Pokemon to fight multiple times, right? Like the current problem statement does not clarifies like what should be done in this case, and I will ask the authors to add that as a condition as well. So the idea is simple. Like let's say we have P4 Pokemon initially in the arena. We use S3 skill to have P7 in the arena, then S4 skill to have P8 in the arena, and then the 7th skill S7 to have P4 again in the arena. And then a fight between P4 and P9 using skill 8 P9 in the arena, and then the rest of the story continues. And notice that the cost of hiring everything is positive over here. So like one shortcut we can take over here is we can completely ignore these parts, and like P4, like we from P4 we directly have a fight between P9. I said because like at the end of the day, like if you try to look at like our cost function is a bit special over here, and like the cost to reach this path would always be less than the cost of hiring all of these Pokemons over here. Because if you look at this edge, right, this edge essentially makes like the eighth attribute of P4 at least equal to the ninth attribute of P9. So the idea is essentially to forget all of these paths over here and just continue directly over here, which is P9. So, like with this, we can conclude that in the optimal sequence of operation, we should never call a Pokemon in arena more than once. So this is the reason why just adding CV cost to all the edges which are coming to V will work absolutely fine for our algorithm. So moving further, like we have added 2 into n into m edges for each skill. So total number of edges in the graph is 2 into n square into m. This algorithm will give the correct answer, but it's too slow for our case, and it will return a TLE verdict over here. So trying to optimize further, let's try one more algorithm. Our current bottleneck is like the number of edges, two n square edges for each type of skills. If we somehow can reduce this figure, then we would be good over there. Like notice what is happening under the hood. Like we have Pokemon P1 using skill, let's say some S1. We take go to we bring PA in the arena. Then using some other skill S2, we bring PB in the arena, and then using some skill S3, we bring PC in the arena, and then using some other skill S4, we bring P4 in the arena. Where S1, S2, S3, S4 skills can be same or can be different. We don't really bother about it at all. And PABC are the different Pokemons which would be like in the path. Like there can be more, but I have taken one simple path to reach the finals. And like to make the terminology simpler, let's say the Pokemons are fighting using the swords. So we can say that PJI PTIJ is the ith Pokemon with the Jet type of sword. Like we have now characterized a Pokemon into M different states, where PI is the Pokemon without any sword, and PTIJ is the Pokemon with Jade sword in his hand. And now he is ready to fight any Pokemon which has Jade skill, which has the same sword with them. So now, if we look at it, initially we had only three Pokemons. Now I have created three more copies, total four copies of each Pokemon. PT11 is the first Pokemon with first type of sword. P32 is the third Pokemon with the second type of sword. P21 is the second Pokemon with the first type of sword. If we split these Pokemons into M more Pokemons, each for a sword of a particular type, we can now add an additional constraint that only Pokemons with same sword can fight each other. And if Pokemons want to switch skills, then they should first drop the current sword to become a Pokemon without a sword and then pick a new type of sword if they want. And if I draw the same graphs again, initially the edges were P1, P2, P3. Now the same graph I have replaced all the nodes like with PT1, PT31, and P2, PT21 for if they are fighting using the first type of sword. Like all the edge cost and everything is same over here. Similarly, for the second type of skill, like PT1 to PT32 and PT22 are the different types of Pokemon we have with that hold the second type of sword. And the cost is essentially the same we had in the earlier example. And like for the third type of skill or the third type of sword, PT13, PT33, and PT23 would be the different types of Pokemon which have third type of sword in their hand. Like all the edge costs are same. Additionally, for free choices between the different types of skills or swords by P1, we can create a zero cost edges between P1, P13, PT11, and PT13. So like this corresponds to the case when Pokemon drops current sword and like picks up the new types of sword. Similarly, we can draw edges between P2, P21, P22, and P23 when second Pokemon drops a sword and takes another sword back. Similarly, for the third type of Pokemon, PT31, PT32, PT33, and P3. Remember how do we handle hiring problem? Like that was the concern here, right? For all the edges U2V, we can do the same thing. We add in cost 3V corresponding to cost of hiring V. We should add this cost only for the Pokemon PV, the one, not PTVJ. Like that is, we try to when a Pokemon try to drop a sword and pick some other sword. Like the new cost should be added to all the Pokemons which are without any sword. The question is why not this one? Like we will come back to it again. Like let's say like we have some cases where like initially a fourth Pokemon with the fifth type of sword is in the arena. Then they fight and a sixth Pokemon with the fifth type of sword comes in, a sword coming, and then the eighth Pokemon with the fifth type of sword come in, and then the path continues. Then this corresponding to a first fight between 4 and 6 using fifth attribute, and then 8 and 6 using the fifth attribute. And if we do not add like C6 on this edge, then the cost of hiring the 6 Pokemon will be missing in this part, right? So the idea is like our cost function is special. Like instead of having the 6 Pokemon in the inventory, we can directly have a fight between 4 and 8 using the fifth Pokemon. As a homework, I would say like try to verify that the direct fight between P4 and P6 will either have the same cost or the lower cost between this case. You can do this by having the six different case, four different cases, either like six different permutation of like the edges between like either the C45 is the highest, or C85 is the highest, C65 is the highest, or like that would be one of three one of these three would be highest, and like among the remaining two, like one of them would be the lowest one. So there would be six different inequalities over here, and you can try to analyze all the six cases to come to the conclusion that a direct fight will either lead the same cost or it will lower our cost. So instead of reducing edges, right now we have increased the number of nodes and the edges both. But if you see why this modified graph with n into m plus 1 nodes and 2 into n square m plus 2 into n into m edges will give us the correct answer, then we are just one more optimization away from getting an AC verdict over here. Hint 1 is like our cost function is special, and like hint 2 is like we should try to reduce the redundant edges over here. Like if we can somehow remove this n factor from here, then like it's perfectly fine time complexity here. So like let's look at j equal to 1 here, like c11, c21 and c31 is this inequality holds. So my essentially claim is like we can remove this direct edge between pt1 and pt31, because like if you see this 4 edge does not serve any purpose, we can go by this path again to get the 4 cost, or if we want 0 over here we can take this path. So instead of 6 edges over here, now we are remaining with only 4 edges here. Similarly, if I look at j equal to 2, like c32 is less than c12 and less than c23. So like we can remove a direct cost between these two. And now if you go by this would pt2 to p31 and p21 to p32, like the cost is essentially the same, which was 8 initially. And if we want to go back to 0, like this path also gives us an 0 edge weight. And similarly, if C13 and C33 and C23 is the case, so like if we go, looks like I messed up a bit somewhere. Like I do not need an edge between 1 and 2 directly. Like this should be 2 and this should be 0. So like 2, 3 is 8, 0 and 0 is 0 over here. So we essentially need only 4 edges over here. So like in general for the jade skill or the jade sword, we can keep only 2 into n minus 1 edges instead of 2 into n square edges and still have same cost between each pair of nodes. For example, if c5j is less than equal to c2j is less than equal to c1j is less than equal to c4j is less than equal to 3j in the sorted order, then we only need the following 8 edges, like pt5j to pt2j, pt1j, pt2j to pt1j, and pt1j to pt4j, and pt4j to pt3j. Like all the reverse edges are of weight 0, and all the edges going further are own difference between them. So now if we want to look at the edge path of edge between like 5j and 1j, we will follow this route, and like some of these two numbers like c2j will cancel out over here, and like the difference would be c1j minus c5j, and like that was essentially also the edge we were adding. And similarly, if we look at p2j and p3j, going on this path will give us like c1j will cancel out, c4j will cancel out, and we would be left with c3j minus c32j. And if we want to go to the reverse, because this is the increasing order, then going to the reverse will always have a path of 0. So initially we had two n square edges, but if we keep this minimal graph, then we only need 2 into n minus 1 edges. And like once we have these, we have drastically reduced the number of edges over here. And now running the shortest path algorithm in this graph will give us like the minimum shortest distance from 1 to j. Now the sword changing argument etc. do not hold, but you can verify that the minimal graph has not increased distance between any two of the nodes which we had in the shortest path. This completes essentially our solution, and if we do, and I will do my code walkthrough for completing the editorial, and I will also add like code link in the description. So this is my code for this problem. First, I have taken all C and A as input, and then I have a solve function which takes C and A. Like M is the number of skills and N is the number of edges, and I have defined one extra constant which is total number of nodes, because each Pokemon has been changed into M plus one different Pokemons. And I have one like let's look at order, like it's now I am iterating on each type of the skills, and I am sorting all the Pokemons based on the increasing order of their skills. And now for each of the Pokemons in this sorted order, I only add edges between the consecutive Pokemons, where like I1 is smaller than I2 and they are neighbors of each other. So like I am denoting the youth Pokemon with this type of skill like JT into M and plus I1, like this is the pair integer which corresponds to the Pokemon which has M type of skills, JT type of skills, and is a copy of I1 Pokemon. Similarly, V. Now I am adding edge from V to U with the difference of their A value over there, and a reverse edge with cost 0. And for each of these Pokemons, I also add the cost of hiring, which is like this is the M into N plus K is the Pokemon without any sword over here. So whenever I reach to the Pokemon which does not have any sword, I add CK as the cost. But if a Pokemon wants to pick up a sword, like the cost for picking up is 0. Now once I have this graph, I need a shortest path from like source, which would be the first Pokemon without any sword, and the destination would be the last Pokemon without any sword. And like the distance, like initial distance is 0, and like this is the Dijkstra's algorithm for finding the shortest path. And at last I am returning the length of path from the source to the destination, and like printing it gives me and a C. This essentially completes my editorial for this problem. If you have any questions in the chat, if any questions, you can put it in the comments. I will try to answer them. I will also paste my slide with some corrections which I have got pointed out in the editorial. And I will also post my Discord's link in the description. So thanks everyone for joining.